All right, so welcome everybody. This is Physics 46. And before we get started with some course information that I'd like to outline for you guys, I'd just like to say a few words about coming back to campus. All right, so for me, this is my first time standing in front of a class delivering a lecture to actual people in almost 2 years. Maybe a little out of practice actually with that. Is that the same for all of you? Has it been about 2 years since you've been in a live lecture setting?
Yeah.
Okay, so on one hand, I'm really excited to be back. I'm glad to be doing it this way. I know a lot of you probably have Zoom fatigue, right? I certainly do. But as you know, there's a COVID surge going on, so we have to make sure that while we're in here, we're being as safe as possible. So everyone is wearing a mask. So that's good. You know what to do as far as that goes. We're just going to keep these on the entire time we're in class. If you're in this class, you've already been vaccinated. So I want to make sure everyone knows that the people you're sitting amongst here are all vaccinated. That should be something to put your mind at ease a bit. However, it is possible that throughout the semester, some of you may get sick, and we're really taking this seriously. We don't want anyone who's showing any sort of symptoms of COVID, even if it's really mild, to be coming into class. All right, so I'm thinking back to my undergraduate days. I know that when I got sick, my sort of tendency was, I want to power through this so I don't miss anything, right? I'll come to class if I have a bit of a cold because, I just don't want to miss anything. That's not the mentality I want you guys to have, all right? Even if you're feeling mildly sick, just sit it out. And know that I'll be recording every lecture, okay? So we're already recording this one, and I'm gonna find a way to make it available for you guys to view after class. I'll have to work out the kinks of that, but later tonight, I'll give you the details on that. It'll be part of the Canvas page, but I just have to set it up. Okay, so do we have any questions about that before we launch into some of the course information? Yeah, go ahead.
What about the labs? Like, say, if somebody...
Right, so thank you for reminding me, I forgot to mention. So for lecture, there's an easy way to record everything, and since the sort of format of the lecture is basically you're going to be taking notes and doing problems, that's something you can easily do at home, right? The lab, not so much. A lot of the labs, especially later in the semester, are going to involve building circuits, which is just not something you're going to have the materials to do at home, okay? So if you miss lab because you're sick, there won't be a way to make that up, unfortunately. Okay, so just the best practice is let me know if you need to sit out a class, and I'll just make sure that you have the lecture material covered. And again, it's for homework, and you can turn that in when you get back, but there's just no way to make up the labs at home, unfortunately. Okay? Any questions on that? All right, so again, if you just came in, get a copy of the syllabus and the worksheet. And we'll start going into some of the course information here, okay? All right, so first thing to mention is just my own contact information. So my name is Dan Carson, and my email is given there, but you already have it because I've sent you guys a bunch of emails already, right? I am going to be holding office hours 3 days a week, and I've decided to do so over Zoom. There's a couple reasons for that, right? So for one, if you can't make it to campus, you can still attend my office hours. That wouldn't be the case if I held office hours in person, right? Yeah, actually that's the only reason. So office hours will be on Zoom. My Zoom link is given here, but it's also something you can find on Canvas and in the syllabus. So all you have to do if you want to come to my office hours is get on a computer and click this link, and you can talk to me in office hours. I recommend using this for homework primarily. This is a pretty challenging class, I'm just going to say up front, and I imagine that the homework isn't always going to come easy. So, don't just sit there by yourself, confused, get help, come to office hours if that is the case, if you need some help, okay? So Tuesdays, 2:30 to 4:30 p.m., I'll have a 2-hour block where you can come and ask me any kind of question you want. Wednesdays, I hold my office hours at night, actually just after we get out of the lab here, which is 8 to 9:30 p.m. And then Thursdays, 2:30 to 4:30 p.m. Okay? All right, so you probably already know this, but let's just go through it real quick. This is how the weekly class schedule is going to play out. Every Monday, we're going to meet for lecture. Sorry, I forgot to change this on the slide. Of course, this is not PS 112, right? This room is HS 143. I had the room switched so we can actually have a camera and microphone setup that's available to us to use. So we're here for an hour and 50 minutes for lecture on Monday, 2 to 3:50. And then right after that, we're in lab, which is in the physical science building, room 120. And you'll only attend lab on Monday if you're in this section, 22228. Okay, so basically all sections are meeting at the same time for lecture, but we split off. Each section goes to a different lab 1 day per week. Okay? So Wednesday, again, we meet for lecture at the same time in the same room, and then lab directly after that if you're in this section, 22229. Okay, Friday, if you're not in this lab section, if you're not in 23552, you don't come to campus on Friday, you don't need to. But if you are in this section, this is when you meet for lab. It's 8 to 10:50 a.m. in the same lab building, which is PS 120. So I actually added this one at the last minute because we had a lot of people who wanted to add the class. So for those of you just coming in, you need a mask, please take one of these in the box and put it on. Oops, the strap broke on it actually. Can you just take one out of the box, please? Oh, we'll get that strap out. All right. Any questions so far? Okay. I need to tell you about the course materials we're going to be using. So I've made kind of a change this semester. If you've taken a class with me before, we've had a textbook called Giancoli that we've used. And actually, if you've taken a class with another instructor in the Physics 40 series, you probably also used the Giancoli textbook. We're going to be switching it up. And the reason for that is I'm going to make this class zero cost, or as close to zero cost as it possibly can be. I mean, you're going to have to buy some things like pencils and papers, a calculator, but other than that, no textbook costs, no lab costs, all right? So for that, we're switching the textbook. It's OpenStax University Physics. We're going to be using volume 2. So all of the material that we're covering is contained in volume 2 of this textbook. Has anyone here, just raise your hand, have you used an OpenStax textbook before? All right, so most of you know what's up. Basically, it's something you can access for free as a PDF on the website here, so you can actually download a copy, or you can just read it within your own browser, if you like. And if you want to, you can actually order a printed copy from this website, but you don't have to do that. That's just if you feel like having a printed copy and that's really important to you, okay? Everything else, mostly I'm thinking lab materials like the lab handouts. We're not gonna have a lab manual. Every time you come to lab, I'm gonna provide you the worksheet that we're gonna go off of, okay? So basically, other than just the things that you use to do problems and take notes, you don't need to buy anything for this class. All right, any questions on that? Okay, has anyone taken a look at the book yet? A couple people? Good. All right, the next thing, kind of pertaining to course materials, is the course website. So has everyone had a chance to take a look at the course website through Canvas? All right, so what you do is you go to canvas.chaffey.edu and you log in. You have your own Canvas dashboard where you see all of your courses in one place, okay? So if you click on Physics 46, that will take you to the course website for this class. And let me just outline some of the things that are going to be there just so you know where to access certain materials. So one really important thing is we'll have a schedule for the semester. Has anyone taken a look at that already? Basically, the schedule tells you each day we meet, what are we doing in lecture, what material are we covering there, and what's the lab. Also, any assignments that are due are contained in the schedule. Another really important use of the website is going to be just course documents. There are a whole lot of course documents, including lecture notes, like this document I'm going off of right now. You can find it on Canvas. Lab handouts, so the instructions for each lab, you find it there too. Solutions to homework assignments. So obviously these are going to be released after the assignment is due, but I do make solutions for all the assignments. You access them through Canvas. That's really something you'll have to do on your own time. We don't really go through the solutions in class, but I just make those available for you guys in case you want to see them, okay? And then of course a grade book. I try to keep it relatively up to date so you know where you stand. And discussion boards, okay? Has anyone used discussion boards in Canvas before? All right, so for this class, it's going to be purely optional. I'm not making any sort of mandatory discussions or anything like that. But it's just a place you can post a question if you have a question and you can't get an answer otherwise, okay? So mostly what these end up being used for are just homework questions, okay? All right, any questions so far? All right, so next thing is a grading scheme. A lot of people want to know about this and how it's going to go. So here's the breakdown. Your final grade is going to be based on the following. You have 3 tests, and each one of them is going to be 15% of your grade for a total between the 3 tests of 45%. Labs, all of the labs together are going to be worth 20% of the grade. And then quizzes, 5%, homework, 10%, and the final exam, 20%. So that's the breakdown right there. I'm also giving you a tentative grading scale. So I'm not going to read off all these numbers. This is on the syllabus, so you can just look at it. But when I say tentative, I could change this, but only in your favor. Okay, so just think of this as like the worst case scenario, and I might lower the cutoffs, but I'm not going to raise them. Okay, make sense? Okay, moving on. This also pertains to grades. I have a policy to drop scores from certain categories, right? So we have the labs, the quizzes, and the homework. So the policy I have is for each one of these categories, I'm just going to drop the lowest score at the end of the semester before calculating a final grade, okay? And let me just tell you what the reason for this is. It's just to give you some leeway in case you need to miss class, in a nutshell. So if you need to sit out class sick, or if you have some kind of family emergency, no big deal, right? That'll just be covered by the 1 drop policy. But I should mention that what is not covered by this policy is any kind of test or exam score. Okay, so you just can't miss a test or an exam, right? If an emergency comes up, just let me know, okay? We'll arrange something, but you can't just not take a test or exam, okay? Any questions so far? We'll keep it moving. All right, let me tell you a bit about what I plan to do for quizzes. Now, if you've taken a class with me online, we didn't really do a whole lot of quizzes in the last couple of years, but this is something that I've done traditionally when we have in-person classes. And I am going to bring it back. So what you can expect as far as quizzes are concerned is throughout the semester, there'll be about 6 to 8 of them in total. So maybe every 2 or 3 weeks, you'll see a quiz. But they'll be really short, so they're not going to take up a whole lot of time. I'm going to give you between 10 and 15 minutes to take a quiz on a typical day when there's a quiz. Also, we're going to do them in lecture, so we'll do them in here, not in lab or online or anything like that. And when I give a quiz, it's going to be at the beginning of class. So again, the reason for that is I just want to make sure everyone's staying up to date on the material and also just coming to class on time. Okay, this is just an incentive to come to class on time. They should be pretty straightforward as long as you're keeping up with the lectures and the homework and everything else that's going on. But if you're falling behind on that, you know, the quizzes might give you some trouble. So just try to stay on top of the class, okay? And another thing is, sometimes I'll tell you when a quiz is coming, but I reserve the right to give a pop quiz, okay? All right, let's talk about homework. So as far as homework is concerned, there's going to be 1 assignment per week. That's just going to be a constant 1 per week throughout the whole semester, except for spring break, of course. And because it's just 1 per week, it'll be relatively long, right? So just to give you an expectation, It should probably take you about 5 hours to complete one of these homework assignments, okay? So what I recommend is don't leave it to the last day. Just chip away at it over the week, a few hours at a time. And I think that's the best way to go. Another thing about homework, yeah, go ahead.
Oh, so there won't be any homework on Wednesdays, just on Mondays?
Yeah, except for next week, because y'all remember we don't have class next Monday, right? So because there's a holiday, next Monday, we're gonna just come to class on Wednesday and the homework will be due then, okay? But typically it's gonna be due on the Monday, okay? Okay, so what I'm looking for in homework, I'm really not as concerned about getting the right answer as working through the problem and not skipping any steps, okay? So I'm mostly just grading for completeness, and like I said, I provide solutions to these homework assignments, and after you get your assignment back and it's been graded, I can tell you where you made a mistake, if you did make any mistakes, and you can see the solutions, okay? So I'm really just concerned with you going through the assignment, doing all the steps, and actually working out these problems, because it's practice, right? That's the whole point. All right, as far as late deductions go, if you turn in late homework, I will accept it, but with a deduction, 15% each day that an assignment is late. Okay? Any other questions on that? All right, keep it moving. All right, labs. So we're kind of just going through all the different components of the course and the different things that factor into your grade. So now we're on labs. Each week, I'm going to provide you the lab handout. So when you come to lab, I'll just pass out packets for that week's lab. It'll contain the instructions as well as place to fill in any of your data or any other things that you might need to do in the lab. But you can always see it ahead of time, right? Has anyone taken a look at this week's lab on Canvas yet? I did post it there. So you can find things on Canvas under Files. So if you go to Files, there's a folder called Labs, and everything is going to be there in advance. So you can take a look before you come to lab. So I think officially our lab room is PS 122 actually. But if you've been to our labs, PS 120 and 122 are connected to each other. And what we're going to do is spread everyone out between those two rooms. Okay, so we'll have 18 people in each lab section, but you'll be split between two rooms. So we'll have about 9 people in each room, depending on how we group up. Okay? The way we're going to work on labs is 2 to 3 people per group, and you'll turn in 1 report per group at the end of the lab section. Now, the reason for this is we just simply don't have 18 lab stations in each room. We have a total of 8 lab stations, so that's why we have to group up. Okay? Another thing about lab is, most weeks we'll be doing some sort of experiments during lab, but on certain weeks, in particular, if we have a test coming up, we'll do a review session in lab. Okay? Any questions on that? Let's keep going. Test and the final exam. Okay, we have tentative dates for the test. Final exam still to be determined. But let me tell you about the upcoming tests. So again, I mentioned each one of these is worth 15% of your grade. The first test is going to cover the following chapters from the textbook. That's 21 through 23. Oh, I'm sorry, guys. These textbook chapters are out of date. These are for the old textbook. I'm sorry. We're actually starting at chapter 5 and then going through chapter 7 for the first test. All right? But that's going to be on February 22nd, Monday, tentatively. Okay? And again, the final exam is TBD, but it is going to be cumulative. All right? So let me just give you an updated version of this once I correct it. Okay. So actually, these are the correct chapters. Okay? So I can just show you here. We're going to start by covering chapter 5 of the textbook. And this is kind of a long chapter. It's really your introduction to electrostatics. And we're going to stay on this chapter for about 3 weeks. So in this chapter, you will learn about electric forces and electric fields and how you can calculate things using those concepts. Chapter 6, you'll learn about something called Gauss's law. Just a show of hands, has anyone encountered Gauss's law in a calculus course before? You may have if you took Calc 3.
I'm very familiar.
Okay, so yeah, especially if you took Calc 3, you would have seen this. All right, chapter 7, we're going to learn about something called electric potential. You may know this as voltage. Okay, so you're going to learn what that's all about. Chapter 8, we're going to learn about something called capacitors and different features of capacitors. These are things that you find in electronic circuits. You probably have capacitors in your pocket right now in your phone. Okay. Chapter 9, we'll learn about electric currents. So before chapter 9, we're learning about basically electric charges that are not moving at all. It's not until chapter 9 that we start to think about what happens when electric charges start moving around. And that's called an electric current. And when you have current flowing in a loop, that's called an electrical circuit. So we're going to learn about that in chapter 9 and learn about circuits in chapter 10. Then basically, chapters 11 through 13 are all about magnetism. So if you like, you can think of all of these chapters up here are about electricity, and these 3 chapters here are different aspects of magnetism. And this class as a whole is about electricity and magnetism. So if time permits, and I'm really hoping we can get around to this, we'll do chapter 16, which is Maxwell's equations. And that kind of wraps all of this stuff up into a nice little package where we see all of the concepts learned earlier kind of fit into a set of really simple equations. So that's what we'll be covering. The last thing to say here before we get into our first lecture is just how you can seek out some help outside of class, right? So really, I recommend reading the textbook as a way of reinforcing the lectures, all right? So there's really nothing I'm going to tell you here in lecture. There's nothing that you need to read in the textbook that you're not going to see here in lecture, right? Just think of the textbook as a way of reinforcing what you've seen in lecture already, okay? And of course, the authors of the textbook have a slightly different way of explaining things than I do, so that might be helpful to see. Feel free to email me. A lot of you have already done that, especially nowadays, again. If you have any kind of concerns about whether it's okay to come to class, just shoot me an email, better not to leave things uncertain. Come to my office hours, like I said. I'd be happy to go through any kind of homework problems with you, help you finish your homework, or if you're stuck on homework, do that. I mentioned the Canvas message boards, right? If you have a question, let's say you can't attend office hours, you can't, have a conversation with me before or after class for whatever reason, you can also use the message boards. So if there's a really hard problem you're stuck on, post a question, and it can be answered by me or by another classmate. So you can actually feel free to jump in if you think you know the answer to something and you can help a student out with really anything that we cover. How many people here are looking around the room and see some people they know already from a previous class? A couple of you? I know some of you 47 people know each other. Yeah, okay, so I really do recommend forming study groups. Like I said, this is a fairly challenging class. Out of all the physics classes offered here at Chafee, this one may be the most challenging, but it's doable, okay? You just have to find the right strategies to study. And one really effective strategy is to work with other people, okay? So if you're stuck on something, really use your other classmates as a resource. So whether you choose to meet in person or online through Discord or whatever, I actually encourage that kind of stuff, okay? The Math Success Center is another good resource for you for tutoring. All right? Do we have any questions? Yeah, go ahead.
Are we going to have SI tutoring this semester?
We do not have an SI leader, unfortunately. Is everyone here familiar with the SI program?
Yes.
Okay. So has anyone had a class in the past with an SI leader?
Yeah.
Let's see a show of hands. Who's done that? Okay. Almost everybody. Yeah, that's a really great program, and it would be nice if we had an SI leader. It's just that the SI program has limited resources, and they tend to identify classes where students need the most help with, overcoming the obstacles of that class. And that tends to actually be 44 and 45. Once people get to this class, having taken a few physics courses, they tend to have better success rates. So unfortunately, that's why we haven't been matched with SI. All right, anything else? Go ahead.
Will you still provide test reviews?
Yeah, we're going to do test reviews. So just so you know, the week before any test that we have, I'm going to distribute a review packet, which has a bunch of problems that are similar to what you might see on the upcoming test. And they cover the same material. And I'll also provide the solutions for that, and we'll go through it during your lab the week before test.
Are the tests still gonna be open notes?
All right, might as well address this one. Okay, so it may have been a while since you've taken a test in the classroom, right? Is that safe to say?
Yeah.
Okay, well, we're going back to traditional test taking here, where you take it in lecture. So basically the day of a test, it'll be taken in this room in the lecture. You'll have the whole time to do it. And, when we were online, what I did was I allowed people to use notes. Okay. But we're not doing that anymore. Instead, the formatting test will be this. I'm going to allow you guys to bring a so-called cheat sheet in that you prepare. Okay, so it's basically a sheet of paper. You can write whatever you want on it, but what I would suggest writing down are all the relevant equations, right? And the actual process of making that sheet is a really good way to study, because as you're studying for the test, you have to go back and review all the lecture notes and all the stuff from the textbook that we covered. And as you're doing that, you're just summarizing everything that you need to have on that one sheet. So that's going to be in place of any kind of open book or open note test. Okay, anything else? Because I think that is it for just going over course policy. So that means we're going to spend the rest of the time here going into the first lecture, which is here. Okay. So again, just a quick comment about how to approach note-taking during the lecture, since, again, it's probably been a while since you've done it this way, right? I'm going to be using lecture slides like this. You can always see these slides ahead of time on Canvas, and what some people do is print them out. Other people download them to a tablet and take notes directly on them on the tablet. You can do whatever you want as far as that is concerned. But one thing I would suggest not doing is trying to copy down every single word on this slide, right? Because you'll have access to this through Canvas later, right? You don't need to get this now. Instead, what I would suggest is take notes on the things that are not on the slide. So sort of additional comments that I might make, example problems that I work out, right? That's something that I'm not going to show you on the slide. I'm going to go to the board and do that. That's when you should be taking notes. I think that's the best strategy. Okay? You good on that? Okay, with that said then, let's launch into our first lecture, an introduction to electrostatics and electric fields. And the material here, like I said before, is coming from the textbook. That's this book here, OpenStax, University Physics, Volume 2, Chapter 5. So let's get into it. So the first thing I'm going to introduce you to is a property of matter called electric charge. Okay? Something you're probably familiar with at some level, but let me just give you a really brief introduction to it, just so we're all on the same page. So one way we can produce electric charge in a material is by a process called charging by friction. And you're actually going to do this in the first lab of the semester. You're going to charge things using friction. That just means we have two materials that are rubbed together, and when they are rubbed together, they acquire this thing called electric charge. So let's take a look at two different cases, okay? In this first picture here, we have two plastic rods. And in this picture here, we have two glass rods, okay? And what I'm showing you is the plastic rods have a negative charge That's what tends to happen if you rub a plastic rod with a cloth. It requires a negative charge. And the glass rods here have positive signs on them. That indicates that they've acquired a positive charge. Now we're going to get into how exactly that happens, what's going on within the atoms of these materials that causes the charge to occur. But for now, let's just say there's a negative charge here and a positive charge here, okay? And if we take two of the plastic rods, again, those are the ones with the negative charge, and put them close together, we'll notice that they repel. So let's say this one is hanging from a string. It can kind of twist in response to any sort of force that's applied to it. You're going to see that there's repulsion here when you have two plastic rods that are charged negatively brought close together. And then same way, if you have two glass rods that are both positively charged brought close together, they'll also repel each other. So the lesson here is anytime you have like charges, like negative and negative, or positive and positive, they repel each other. On the other hand, let's look at this case here, where we have a negatively charged object and a positively charged object. They attract each other. Okay, so you already know this, right? Opposites attract, like charges repel each other. Okay, that's just the most basic thing we can know about electric charge. So it's actually Benjamin Franklin, the guy on the money, that proposed sort of a theory for electric charge. And his proposition was there are just two types of electric charge, not three, not four, just two types. And they're just given the names positive and negative. Okay, so just keep that in mind. Positive and negative, this is just how we label things. This is just how we account for the fact that there are two types of charge. We just call one positive, we call the other negative. And as we're going to learn later on, like midway through the semester, Franklin kind of named these the wrong way by mistake. But that's a story for later. So the type of charge that a plastic rod gets when it's rubbed with a cloth, we call that negative. The type of charge that the glass rod acquires when rubbed with a cloth, we just call that positive. And again, like we found out earlier, opposites attract and like charges repel. There's also something really important to state here about electric charge. There's something called the law of conservation of electric charge. So you've probably seen in the past, right, different conservation laws. What's an example of a conservation law in physics that you've seen?
Nothing can be created or destroyed.
Okay. Someone else said?
Energy and kinetic energy are conserved.
Right, so there's the idea of conservation of energy. This is something like that. The law of conservation of electric charge says that electric charge is not something that can be created or destroyed. The only thing that can happen is charge can move from one place to another. You can transfer some charge from one object to another, but there's nothing you can do to just make charge that exists in the universe disappear or come in out of nowhere. That's the idea. So all that happens is charge moves around, but the total amount of charge out there in the universe isn't constant. Make sense? Go ahead.
When it transfers, it doesn't like lessen, or if that makes sense, like.
So yeah, it doesn't, and we're gonna get into some of those details now about how this transfer works. So you may have heard of conductors and insulators as a distinction we can make about what type of material we're dealing with, right? So what I want you to do is just consider two metal balls, and to start off, one of them is going to be charged. Let's just give it a positive charge. Let's just say that's what it has. And the other one is neutral. So that means it doesn't have any overall electric charge. We could say the charge is zero here, in other words. And what we're going to do is we're going to connect them. Okay? In one case, we're going to connect them with a metal nail like this. In the other case, we're going to connect them with a piece of wood. And the metal nail and the piece of wood are different in the sense that two different things happen in these cases. Okay? If we connect them with a metal nail, what's going to happen is some of the charge that started off here is going to be transferred over here. And it's actually moving through the metal nail. But if we do this with a piece of wood, no charge moves over. Okay? This one that starts off neutral stays neutral, and this has the same amount of charge that it started off with. Okay, so this is what I was talking about earlier. Charge can move from one place to another, but we still have the total amount that we started with. So that just illustrates the difference between a conductor and an insulator. A conductor is a material where charges are free to move. So this metal is a good conductor because it can carry charge from one place to another. But this wood is not a conductor. It's actually something we call an insulator because charge is not free to move. In other words, whatever charge there is just in a fixed place. It doesn't get to move around in an insulator. So generally speaking, any type of metal is going to be a good conductor, okay? And pretty much everything else is going to be an insulator. And again, this is a bit of an oversimplification. There's something called semiconductors also, and it's not like it's just a binary thing where you're either a conductor or an insulator. It's kind of a spectrum, okay? But this is a good way to think about it to start off. Okay, so now let's talk about, we have this idea of charge, that we have positive and negative charge, and charge can move around, but it can't be created or destroyed. It's a conserved quantity, okay? So let's talk about exactly what's going on at the atomic level as far as electric charge is concerned, okay? So we're all familiar with this sort of model of an atom, right? Where we have a nucleus and some electrons orbiting the nucleus, right? Can anyone throw out a quick explanation of this? What is it that makes an element like oxygen or nitrogen distinct?
The number of protons in the nucleus?
Yeah, exactly. So what makes an element distinct is the number of protons in its nucleus. So actually we have the periodic table right over here, don't we? These elements are ordered in terms of that number. So hydrogen over here has 1 proton in its nucleus, and helium has 2, and so on. So that's what makes an atom. That's what makes an atom have its own unique identity. So the nucleus is a really dense collection of protons and also neutrons. Okay, so protons and neutrons can be found in the nucleus, packed very, very tightly together. There's a lot we can say about these particles, but for now, let's just say that a proton has a positive charge and a neutron has no charge, as the name suggests, right? Electrons are not found in the nucleus. They're found moving around the nucleus, and these particles carry a negative charge. And another thing just to note is that electrons are very low mass in comparison to either the protons or the neutrons. So basically, almost all of the mass is contained here in the nucleus. Very little of it is in the electrons. In fact, oftentimes we just ignore the mass of the electrons because it's so small. Okay, so we have positive protons in the nucleus. We have negative electrons outside of the nucleus, but bound to it. And one thing you should know is that protons and electrons have equal but opposite charges. Okay? So not only is one positive and one negative, but in terms of absolute value, they have the same charge. Okay? One is just the negative of the other. So this is something I guess I could just note for, since it's on the slide. The variable Q is what we use for electric charge. Okay, so from now on, if you see Q, whether it's lowercase or uppercase, that's usually talking about electric charge. So this is saying Q electron equals minus Q proton. Okay? So in a typical atom, we're going to have equal amounts of protons and electrons, right? So in other words, let's take, I don't know, nitrogen over here, right? On the periodic table. How many protons do we have? 7. Okay, and if this is a typical nitrogen atom that you'll just find in the atmosphere, let's say, it's also going to have 7 electrons. So what is the overall charge of that nitrogen atom? 0, right? If you have equal numbers of positive and negative charge, you have 0 charge. So most atoms that you find out there in the world are just neutral because of that, okay? However, it is possible to have something called an ion, right? We're familiar with this from chemistry. If you've taken chemistry, an ion is just an atom that has either gained or lost an electron. So then it may have too few electrons to be neutral, or maybe too many, right? It may have an excess of electrons. So whatever the case may be, an ion doesn't have zero charge, right? It actually has some non-zero charge. And that's what an ion is. I just made a quick note over here on the slide about what's going on in the nucleus. So I'll just touch on it real quick, okay? If we have two protons, let's say, positive and positive, what do? Do they attract or repel? Right. So these two protons in a nucleus will repel, right? So why do they stay together? Well, the neutron is neutral, right? It doesn't attract or repel.
Because of the strong nuclear force.
Yeah, okay, so that's why I put this here, right? There's something else going on here. It's called the strong nuclear force. We're not going to get into that, but just want to make a note of that. There's something else going on that holds these things together in the nucleus. Okay? All right. So for the most part in this class, we're going to be concerning ourselves with solid materials, okay? The way electric charge moves around in a liquid or a gas actually can be a little bit more complicated, and if I'm remembering correctly, I don't think we really covered that. So for the most part, when we talk about electric charges in a material, we're talking about solids. So let's get into what is going on inside of a solid material with electric charges. Okay, when you have a solid material, the atoms that make up that material are arranged in something like a lattice like this, where each atom has its own position. And it might be nicely organized like this, or it might have a more complicated structure. But the point is, each atom has some position, and it's basically fixed in that position. All right? If it were a liquid or a gas, then the atoms could just be moving around wherever they want to go. But that's what makes a solid, is that each atom is basically fixed. Okay? Now, the positive charges in an atom, they're in the nucleus, right? We're talking about the protons here. They're inside of the nucleus, aren't they? And they're basically stuck. They can't move large distances. If you have a solid material, there's no way a proton is going to go from over here to over here. It's not happening. But sometimes, if you have the right type of material, the electrons are a bit more mobile. They have the ability to move around. So that's what we have in a conductor. In a conductor, some of the electrons in each one of the atoms is not actually bound up. It's free to move around. It's what we call a free electron. And those free electrons can just move anywhere they want to go within this lattice. And that's really what makes a conductor, is that it has these free electrons which can move throughout the material. In an insulator, you don't have that. Every single electron is just bound to an atom, and it's not free to move around. Okay? Now that may seem a little vague, but the reasons for that are really, really complex and kind of beyond the scope of the course. So that's why we just classify things in these two ways. We good on that? Just by a show of hands, who here recently took 45 or 47? Pretty much everybody, right? Well, do you remember studying thermodynamics in these two classes?
Yeah.
So what does it mean for an object to have heat or be warm or hot? It just means the atoms in that material are jiggling around, okay? So technically, I say these atoms are just stuck. They don't move, period. It's not quite right. They sort of jiggle around in place, but the point is they don't move large distances, okay? So are we all good on that? So the takeaway points are we have free electrons moving around in a conductor, and we don't have that in an insulator, okay? And basically, that's how charge moves around in solid objects. It's just electrons. Protons are not really moving around. Okay, so we're going to touch on a lot of conceptual stuff here, just so you're aware. We haven't even written down a single equation yet, but it's really important just to understand what charge is and how it kind of manifests in different materials, okay? So to that end, we're going to talk about something called polar molecules. Okay? So a molecule is something that consists of more than one atom bound together, of course, right? Let's take chemistry. We know this. And in some molecules, well, let me back up actually. In a molecule generally, right, the atoms in that molecule are sharing electrons. That's why they're bound together. They're sharing the electrons contained in the individual atoms. And in some molecules, the electrons are shared pretty much evenly. So in other words, let's say I have an O2 molecule, 2 oxygens, right? The electrons that are being shared between those 2 oxygen atoms don't really have any preference for one or the other, right? They're just as happy to be on one of those atoms as the other, right? In other molecules, that's not the case. In other words, the electrons are unevenly shared between the 2 or however many molecules there are. And that's what we call a polar molecule. So a polar molecule is a molecule that overall, if you add up all the charge in it, it's neutral, right? Because it has the same number of protons in it as it has electrons, but the electrons are not evenly shared. In other words, the electrons have a preference to be on one side of that molecule or the other side. And because of that, let's say we have electrons in a water molecule, which are shared between the oxygen and hydrogen atoms in the water molecule. The oxygen actually has a slight negative charge because it tends to attract the electrons a little bit more than the hydrogens. So in other words, just think of it this way. Electrons are sort of hanging out around the oxygen a bit more than they're hanging out around the hydrogen. And because of that, there's a slight negative charge here and a slight positive charge down here. Okay, does that make sense? So if we have an uneven sharing or an uneven distribution of charge, what you're going to have is a positive side and a negative side. Okay? So, I didn't check the weather today. I'm not sure how humid it is, but in today's lab, and the lab that you'll do this week more generally, we're going to be creating static charge, right? So we're going to be basically creating charge by friction, rubbing one material against another. And one thing that gets us, one thing that makes this lab kind of hard sometimes is if it's very humid outside. And the reason for that is water molecules, because they again have a positive and a negative side, can be attracted to charged objects, right? So like if I just take a positively charged object and put it here on a humid day, it's going to attract a lot of water molecules, which can actually neutralize that object. So that's something we might have to deal with in lab. That makes it a bit harder to do the experiment. Okay, so any questions about this, what a polar molecule is? Again, just it's a molecule with a positive side and a negative side. Okay, so, yeah. So this is our first question for the class. I'm going to give these from time to time. These are questions that I want you guys to work on for a few minutes while you're here. I don't want the whole lecture to just be me talking at you. I want to give you a break and give you something to do at your desk, okay? So here's the question. We have a positively charged glass rod right here, okay? And then over here we have a metal sphere, which doesn't have any overall charge, okay? In other words, there's an equal number of protons and electrons on this metal sphere. So my question for you is, what happens when we bring the two close together? Is it going to be that there is no force between them? Is it going to be that they will repel each other, or will they attract each other? So those are your options, okay? And what I'd like you to do is take a minute, talk with the person next to you, and see what you think, okay? And then we'll put it to a vote by a show of hands in about a minute. Okay, so go ahead and do that. That's like a good first thought, but think about the fact that it's a metal sphere called a conductor. So it might help you to just draw a little picture. What is going to happen to the electrons? Because the electrons are free to move around, right? In that conductor. And I will try to think about how that happens. It is kind of a surprise. Okay, let's reconvene. I know you probably have a lot of good discussion going, but I just want to see by show of hands. You might not be 100% sure in your answer, but you know what are you leaning towards the most? Who says no force between them? Okay, who says they repel? Who says they attract? If you answered they attract, you're correct. Now, so it's a little bit more complicated. The point here is there's a little bit more going on than just saying this is positive, this overall has no charge, so they can't attract. It's not that simple. Okay, that's what I'm trying to say. And the way I'll show you that that's the case is by just drawing a little picture. So when I work things out, when we do examples, I'm going to be using the doc cam. This way we can capture everything on video here. But let's just draw a picture, okay? So remember, I have the positively charged rod right here. And then I have the neutral sphere, which is made out of metal, right? So this is important. It's a conductor. And what do we know about conductors? Yeah, they have free electrons, right? So an electron, let's say, I don't know, over here in the conductor, doesn't have to stay there. It can move. And is there something that's going to make that electron move?
The positive charge in the rod.
Yeah, the positive charge on this rod is going to be attracting electrons in this conductor, isn't it? Yeah, and so when they're attracted to the rod, which direction are they going to move it? Left or right?
Towards the rod.
Yeah, so in other words, do you see that? Electrons will be pulled to this side of the conductor. Now, remember, charge is conserved, right? What is the total amount of charge that we have on the sphere? It's 0. Mm-hmm. That's right. So what does that mean about this side of the sphere? This side of the sphere is positive. In a way, you can think of it this way. The electrons are moving this way. That's our electron flow, right? So before they moved, there were an equal number of protons and electrons over here, so it was neutral. But now, we have an excess of electrons over here, so it's negative. And we lost some electrons from this side, right? So now it's going to have a positive charge. Do you all see that? It's really important to see that. So because the electrons have moved over, essentially, now with the metal sphere, we have a positive side and a negative side, okay? So I'm going to draw something else, right? So let's consider the interaction between the positive charges here and the negative charges here. What kind of force will exist between them, attraction or repulsion?
Attraction.
Okay, so check this out. What I'm going to do is I'm going to draw sort of like a force diagram. You're familiar with this from Physics 45. There's a force of attraction that the rod experiences towards these negative charges, okay? So what am I going to call that? I'm going to call that F negative. Okay, let's consider another interaction. Let's consider the interaction between these positive charges on the rod and then the positively charged side of the sphere over here. Is that going to be attractive or repulsive? That's going to be repulsive. So in other words, the rod is going to be repelled away, right? So you have this rod being pulled in two different directions, right? If it was being pulled in two different directions by the same amount of force, we would say there's zero force, right? Because they would cancel. But is that the case? Are these two forces equally strong?
No.
Okay. Does anyone know the reason for that? I haven't told you the reason for that yet, but you might already know.
The distance?
Is distance, yeah. It has everything to do with distance. You see this? The attractive force is coming from charges that are kind of close together, right? And the repulsive force is coming from charges that are further apart. Distance matters. The further apart the charges are, the weaker the force gets. That's something we're going to learn about. And so because of that, let me just write it this way. F negative, that's the one that's attracting, is bigger in magnitude. So I'm writing the magnitude of this force is bigger than F positive, which is repulsive. And guess what happens? The attractive force wins out, and so overall there is attraction. And you're going to see this in lab. This is how it works. Okay? Yeah, go ahead.
Do we always label attractive forces with a negative sign?
No, I just kind of, there's nothing special about the way I labeled this. I'm just trying to show that the negative sign just means I'm talking about the force on the rod due to these negative charges. That's the reason I put that there. Any other questions about this example? Go ahead.
What happens if they touch?
Okay, good. So if they touch, which is, we're going to get to that, some of the electrons can go onto the rod. Yeah. So you can, in other words, you can charge something by directly contacting it. We'll talk about that in a second. Yeah, in fact, switch over. There we go. Let me know if I ever have the wrong thing on the screen. I'm trying to manage a lot of things here. I'm trying to write stuff on the document cam. I have the lecture slides going and I'm recording all at once. So if I don't have the right thing up on the screen, just let me know, okay? All right, so there are basically two sort of processes here, ways to charge things that I want to go over with you. And the first is what Esteban just asked about. It's called charge by conduction. So this is when you have two objects that may be charged in some way. And charge is just transferred from one to the other by direct contact. Okay? So in other words, you just touch something and then the charge is transferred to you. Can you think of an example of where that happens in real life? You ever touched a charged object before? What happens?
Like static shock, like a touch metal.
Yeah.
That's part.
Perfect. Yeah, like if you walk across a floor, like a carpeted floor, you might build up some charge in your body, and you touch a metal doorknob and it discharges, right? That's really just charge by conduction. It's where charge is transferred from one object to another just because they're directly touching each other, direct contact. So an example of this would be here. We have a neutral metal ball, which is right here on the right side. And then we have a positively charged metal ball over here on the left side, okay? So charging by conduction would be the sort of process where we make the two touch and electrons flow off of the neutral ball into the positively charged ball, and the charge basically ends up spreading out a little bit more. You see that? If we take electrons from here, move them over here, this will be less positive than before, and this will end up with a positive charge because it lost electrons. Electrons flowing from one object to another, when they touch, that's charged by conduction. Conduction just means flow of charge, okay? Charge by induction is the process we saw in that last example, okay? So charge by induction is like this. Charge by induction happens when you have a charged object nearby something, and that causes the positive and negative charges in that object to separate out. That's exactly what we saw in the example. Again, so this is the same exact example. I'm just going to go through it again because I think it's important to remember how this works, okay? So again, we have the positively charged object right here. And we bring it close to a neutral object, which is, in this case, metal, okay? So it's a conductor. The electrons are free to flow around within this conductor. Now what happens? As we saw, electrons in the conductor are attracted towards this positive object. That's the nature of electrical attraction. But when that happens, we see the charges separate out. In other words, we have a negative side over here and a positive side over here. So before it was just completely neutral everywhere, but now we have a negative and a positive side. We've separated out the charges.
So if you pulled the rod away, would it go back to like its neutral state, or?
Yeah, no, that's a very good question. So yeah, the only reason there's a positive side and a negative side is because the rod is there. So let's remove the rod, right? What's going to happen? These charges get attracted back this way, right? So yeah, that would go away if you move the rod.
Is it possible to negatively charged rod as well?
Yeah, you could flip everything around and it would be the same picture, just with a negative. Okay, so again, they're not actually touching each other. This is important. But what happens is we separate out the charges. And as a result of that, we have this attraction, right? Because as I showed you before, the negative charges in the sphere attract the rod, so that's F negative. And the positive charges in the sphere repel the rod, because they're the same type. But overall, the force is attractive when we consider how these two add together, okay? So that whole process that we just outlined is called charging by induction. Does that make sense? Okay. Okay, so just to recap, we saw that at least in a metal, where we have a good idea about how charges move around, right? That we can have this process called charging by induction. Okay, so we saw what that process is. I'm not going to explain it again. But my question for you is that process possible? Can we have charging by induction in an insulator? So don't think about like a metal. Think about, I don't know, like wood or something like that. So two possible answers, yes or no. And also just discuss it with the person next to you for a few minutes, just so we can vote on it later.
That's the only thing I can think of what he said.
All right. So let's put it to a vote. Who says that yes, that this process we outlined is possible with an insulator? Who says no? So the answer is yes. You might, okay, so there's a pattern here, right? The questions have an unexpected answer, right? So let me show you how. Or actually, before we even go into this, let me just explain something you've undoubtedly seen in your life, right? Have you ever taken a balloon, rubbed it on, I don't know, some cloth? What happens? It's sticky now, right? It can stick to your hair, it can stick to the wall, it can stick to whatever. Is anything involved in that conductor necessarily? I could take the balloon, rub it against my arm, and stick it to the wall. I could stick it to a piece of wood. I could stick it to myself. None of those are conductors, right?
I have a question, please.
Uh-huh.
Yeah, the thing is that there was talking about the induction. And when he was talking about the induction, you mentioned that they are not touching together.
Yeah, but I'm just,
Say no.
yeah, but here, the balloon is just a charged object, right? If I took a balloon and, I don't know, maybe took a bunch of pieces of paper, I could attract those pieces of paper, even if they're not touching. I could attract them from a distance. And that's exactly what we're talking about here. So let me show you exactly what I mean over here. Okay, so same basic idea as before. We have the idea is we have a charged object, and we're bringing it next to a neutral object. And what I want to convince you of is they can still attract, even if the neutral object is not a metal, or it's not a conductor. Okay? And the reason for this is polar molecules. We talked about this before, right? So remember, some materials, like water is a really good example, the molecules are polar. What does it mean to be polar again?
It's got a positive and a negative side.
It's got a positive and a negative side. That's what it means to be polar. So all I want you to think about is, let's take some charged object and bring it near a material where the molecules in that material are polar. They have a positive side and a negative side, okay? Now, that material could be an insulator, right? It doesn't necessarily have to be a conductor, but the point is we're saying it's got polar molecules. Okay, so normally, if there was nothing, like no charged object around, these molecules would just be kind of randomly oriented. In other words, maybe for the first molecule over here, the positive side could be facing up and the negative side down. Maybe for this one over here, the positive side is off to the right and the negative side is off to the left. Basically, they're just randomly oriented, okay? But if we bring a charged object nearby, now they line up in a certain way, right? Because think about it. The negative side of the molecule, in this case, is going to be attracted to this positively charged rod. So in other words, it's going to face so that its negative end is towards the rod. And it's going to face so that its positive end is away from the rod. You see that? Just by the way electrical attraction works, we can see how the molecules would line up in this way, okay? And now the same exact argument that we made earlier applies. The negative charges here are closer to the positively charged rod. The positive charges over here are further away from it. So overall, there's an attraction going on, okay? And actually, the argument works the same way if we flip everything around. So in other words, let's imagine we have some kind of insulating material here, and it's totally neutral, but we bring a negatively charged object near it, okay? Now what's going to happen? The molecules are going to line up so that the positive ends are facing this way. They're attracted towards the negative rod, aren't they? So again, because of that, everything orients itself in a way that there's still an overall attraction. And let me just, again, show you examples of where that kind of thing is going on. So the balloon example, right, where you take a charged up balloon, bring it next to something that's neutral, like, let's say, this cat. You can make the cat's hair stand on end, can't you? This is what's going on in that sort of situation. Or you can take, like a comb, charge it up, you can pick up little bits of paper. Even though those bits of paper aren't conductors and they don't have any charge on them, there's still attraction, okay? So that's charge by induction in action, okay? Any questions here? Yeah, go ahead.
So when you have a situation, the electrons don't move around the object, they just basically rotate about themselves to face the attractive force?
Yeah, so the molecule itself is not going to be moving a huge distance. It's just the molecule itself can sort of reorient itself. And again, this kind of thing happens all the time. These are examples. All right. So we've made a lot of progress so far. The next thing we want to talk about is grounding of charge, which is probably something you've heard before, right? When we ground a charge, what are we doing? Well, to sort of set the stage here, we're going to think about the Earth itself, okay? The Earth itself is obviously pretty large compared to any circuit you could build, right? Or any sort of object you could put on the table. It's a pretty big object. What is the Earth made out of? A lot of different stuff. What kind of materials? A lot of them are metallic. Yeah. In other words, the Earth itself is a pretty good conductor. It's the kind of thing that can easily accept electrons or give up electrons. Electrons freely flow through it, is what I'm saying here. So, because the Earth is so large, it's basically a limitless source of electric charge, okay? There's more electric charge sitting in the Earth than we could ever need for any circuit we ever built, okay? So the point here is when we ground an object, all we're doing is we're connecting it to the Earth by some kind of path that allows charge to flow, right? So there's a symbol that tells us something is grounded or connected to ground, which I'm showing you right here. Just remember this symbol. If you see this symbol attached to something in a diagram, that just means that object is grounded and it has a connection to the Earth, okay? So what I'm going to show you next is an example of grounding charge and what happens when we ground charge. Okay, so here's the scenario, okay? We have a positively charged rod right here, and we bring it next to a metal sphere. We already saw what happens there, right? This is just a review. Electrons in that metal sphere get attracted to the positively charged rod and sort of biases them towards the left side and makes the right side positive. Okay, so we have this sort of separating out of the charges, okay? But now let's imagine this, okay? Let's imagine we have this scenario already set up, and then we ground the sphere. In other words, we take the sphere and we connect it to the Earth. I mean, you can quite literally imagine this. This is how grounding works in a typical circuit. You're just taking some kind of metal wire and just taking that, connecting it at one end to the object, and putting the other object in the ground, okay? What can happen then? Well, electrons can flow up from the ground to the object, or vice versa. Both of those things can happen. In this case, what's going to happen? In this case, electrons are going to come up to be attracted to this positive end, right? If electrons are free to move, they would tend to be attracted to this positive end, and that would neutralize this positive end. So we take, this end that was overall very positive and make it less so because electrons have come in. So that's grounding charge. That's what it is. Go ahead.
For the other slide, it was about the protons can't come up from Earth.
Yeah, so again, it's important to remember, I'm glad you asked, in all of these examples, we're talking about electrically charged objects that are solid. It's only electrons that are moving around, okay? But here's the thing. If electrons come in to something that's neutral, that now becomes negative because it has an excess of negative charges, right? And if electrons leave something that's neutral, that's now positive because it has now more protons than electrons. So it's only electrons that are moving around, but you can still make things positive and negative because of that, okay? All right, so I have a question for you guys. Again, this is another one just to think about how this process would unfold, what would happen in this scenario, okay? And so we're going to do it at our desks, and then we'll go through it together like the last one. So consider the process shown on the right. We have charges, there's a metal rod right here, And I'm not showing you the charges on the metal rod. Part of figuring out what's going to happen is to sort of draw this picture for yourself and sketch out where the charges are, okay? But anyway, we bring a negatively charged plastic rod towards the metal rod, which is, by the way, connected to the ground. Then what we do is we disconnect the metal rod from the ground. And then lastly, we remove the plastic rod. So my question for you is, what's going to be the final result of this? Like, is there going to be overall zero charge on this metal rod when it's all said and done? Is there going to be positive charge, or is there going to be negative charge? That's the question for you. And the way I would approach this is talk about it with the person next to you, but also copy down this picture and try to draw how charges are moving around within the metal at each step. If you get it right, you should be able to figure out what you're left with at the end. Okay? So take about 4 or 5 minutes to think about this one.
That's why I think
Okay, so I see the discussion is dying down a little bit, so we can now put it to a vote, right? So who says that after all this stuff happens, we have zero charge on the metal rod? Who says we have positive charge? Who says we have negative charge? If you said positive, you're correct. Let's go through it. I'm going to kind of go through a similar process as before, where we draw a detailed picture showing where all the charges are going at each step. That's going to be helpful, okay? So what do we have at first? We have the plastic over here, which is negative. Okay, and we bring it nearby the metal rod, which starts off neutral, right? But, hold on a sec. We have it connected to ground. So I want to just ask you the question. In this scenario, what's going to happen to the electrons in the metal? Remember, it's the electrons that get to move around. So if they're going to be pushed one way or another, which way are they going to be pushed?
Towards the right side.
Yeah, electrons in the metal are going to be repelled from this negative charge, right? And where are they going to go as a result of that? They're going to go towards the right side, right? Now some of them, I'm not saying every single electron, but some of those electrons are going to be pushed into the ground. Okay, can you see that? Just by the mere repulsion of electrons from this negative charge, some of those electrons are going to flow to the ground. Okay? And when that happens, okay, when these electrons flow to the ground, what kind of charge are we left with on the metal? We're left with positive charge, right? Because if we start off neutral and we lose some electrons, charge is conserved. So we have now positive charge, don't we? So that's what we have. We good on that? Okay, so yeah, go ahead.
Oh, the electrons wouldn't come up from the ground, so it wouldn't come from the earth. It would.
So in this case, yeah, in general, when you connect something to ground, the motion can go either way. Just in this specific case, because of that repulsion, that's the way they're moving. Okay? So in other words, if the plastic rod were positive, it would go the other way. Yeah. All right, so now what we do is the electrons have flowed to ground, the metal rod has become positive, and now we're going to disconnect from the ground, right? So the plastic, nothing changes there, right? Just negative. The metal, that's positive, isn't it? Still positive even after we disconnect from ground. But the reason I draw this is, at this step, there's no outside source of electrons, right? So like, there's no way for electrons to come back into the metal once we've disconnected it from the ground. Do you see what I mean? Because that's the whole reason there's that ability, is because we connected it to ground in the first place. So, as a last step, when we just remove the plastic, guess what? We still have positive charge on the metal. There's just no way for it to leave once we've disconnected from the ground. Okay, so the answer is, you get positive charge on the metal. Okay? So I'm going to ask you a follow-up. It's a very similar kind of process where, things like this are happening, but I'm going to switch the order around, and it's going to change the answer. Okay? So let me show you what I'm talking about. So in this example, this follow-up, this is a different scenario. So here's what we do. We start with a metal rod, which is neutral, and connected to ground, just like before, same starting point. We bring the plastic rod towards the metal rod, just like before, but then we switch the last two steps around, okay? So in this step, we remove the plastic rod, so it's no longer near the metal, and then in the final step, we disconnect from the ground, okay? So those are the things that happen in this process. And the question I want you to think about is the same. What are we left with at the end? Are we left with 0, positive, or negative charge? Okay, so take another couple minutes, think about this one, and then we'll go through it.
So you said just
Okay, let's put this one to a vote. Again, if you're not quite sure of your answer, just go with what you're leaning towards the most. Who says zero charge? Cool. Who says positive? Who says negative? It's going to be zero. So most of you are seeing how this works, right? So again, just so we're covering all our bases, let's go through it real quick. So remember, the process is, just copy it down again, plastic here, which is negatively charged, and metal here, which starts off neutral. However, because we're bringing the plastic rod towards that neutral metal rod, which is connected to ground, so the starting situation is pretty much the same as before. Just like before, the electrons flow to ground. Okay? And just like before, that leaves the metal positively charged. Okay? So nothing new here. This is the same thing we saw before. But the thing that happens next is we're going to remove the plastic rod. So we're just going to move it far away from the metal so that it's no longer really exerting any kind of noticeable force on it, right? So now, plastic is gone. We have the metal connected to ground still. This is important. It's still connected to ground. And, for the time being at least, it's positive, right? What's going to happen now?
It's gonna flow back in.
Yeah, see, basically all that's happening now is electrons are flowing right back. Because, again, plastic rod is gone. The only thing that's happening is electrons from the ground can be attracted to this positive metal. And that's why they flow back up. It's just that positives attract negatives. It's really the whole, idea behind all of these. So electrons now flow back from ground after the plastic is removed. Okay? And when they do, they neutralize the positive charge. Okay. So then if we, as a final step, remove the metal from the ground, well, it's neutral, it stays neutral. Okay? So the answer is neutral. And most of you saw that. Okay? So those were a couple examples just to get you thinking about this stuff. It's worth noting that so far we have not written down a single equation, right? So there are some equations that explain quantitatively what's going on here, but for now, we're just interested in a qualitative picture about how charge moves around. So hopefully that's starting to come into view. And our lab is going to be all kinds of experiments like this, okay? And speaking of the lab, actually, we're going to be using a device in the lab called an electroscope. So let me tell you a little bit about electroscopes. An electroscope is really just a device that is used to measure electric charge. And here's how it does that. So the electroscope looks something like this. Here's a schematic. We have a metal object, usually like a metal bulb, sticking out from the electroscope. So you can touch things to this to introduce charge to it. But then inside the electroscope, which is behind a glass case, you have two leaves, two metal leaves. In this picture, they're gold, but it really can be any kind of metal. It doesn't matter. You have two metal leaves connected to this metal bulb on the top. Okay, so in other words, This is all just one big conductor. Charge can go from here down to here and back, okay? Now, if we charge the electroscope, if we put some charge on it, just think about what's going to happen. Doesn't matter if we make it positive or if we make it negative. The leaves are going to separate, okay? Let's see why. If I put positive charge on this leaf and positive charge on this leaf, in other words, we're putting the same kind of charge on the electroscope. Well, we have two positives and they separate, okay? If I put negative charge on the electroscope, I'm going to have negative charge here, and guess what? They'll still separate. So quite literally, you can charge up an object, just touch it to the electroscope so that the charge gets transferred, and when you do that, you see the leaves separate, okay? And that's called charging by conduction, when we just touch something that's charged to the electroscope, transfer it onto it, and see the leaves separate, because there's the same type of charge on each leaf. Does that make sense? So if we put some charge on it just by direct contact, the leaves are going to separate. You'll see that in lab. We can also do charge by induction. Remember, this means we don't actually make direct contact. We just hold a charged object near the electroscope. We don't touch it, just hold it nearby. Okay? And let's just think about what happens. Let's say that object that we bring near the electroscope is positive. That's just the example here in picture A. So what is a positive charge going to do to electrons in the metal of our electroscope?
It'll attract them.
It'll attract them. Electrons are going to move up this way to be attracted. You see? And just like before, if we have electrons leaving some area, so they'll be leaving the bottom and going towards the top, that's going to leave the bottom side where the electrons have left positive. Electrons go away, you end up positive. So basically, we have a positive side down here and a negative side down here. But because we have positive charges down here, there's going to be repulsion between the two leaves, just like before. Does that make sense? So basically, if we charge up an electroscope, you can see the leaves separate. And how much they separate tells you how much charge there is. They'll separate a lot more if there's more charge. They won't separate a lot if there's just a little bit of charge. Does that make sense? Okay. So we're going to cover units of charge as our last topic for this lecture. And then in the next one, we're going to get into some of the equations that underlie all these ideas. Okay? But let's get into units. Let's actually start for a minute to get quantitative about what we're talking about when it comes to charge. Okay, you're all familiar with the SI system, right? Let me just review. In the SI system of units, we have kilograms as our fundamental unit of mass, meters for length, seconds for time, and Kelvin for temperature. We probably won't be dealing with that one very much in this class, but those are some of the base units. Now we have this new type of quantity called electric charge. And we can actually put a number to it. We can actually measure it precisely, and it has a unit, just like anything else we measure. That SI unit is called a coulomb, named after someone named Coulomb, who I'll tell you about next time. But that's our fundamental unit, and we'll be seeing this basically throughout the rest of the semester. So I think the best way to introduce you to the coulomb is to compare it to some charges that we've already talked about. For example, remember, the charge on a proton and the charge on an electron are equal in terms of the size, but they have opposite signs, right? One is positive, the other is negative. Turns out you can't break charge down into smaller amounts than that. The amount of charge that you find on an electron is the smallest amount of charge that is possible. You can't take an electron and chop it up into smaller charges, okay? So because of that, we call this the elementary charge. It's the smallest amount of charge that can exist in isolation in the universe. And we call this E.
What about quarks?
That's because I said in isolation. Quarks don't exist in isolation. That's a big point, yeah. Exactly.
Yeah.
So yeah, you'll never find a single charge in isolation with something small. So okay, what is that charge? For the electron, we say Q, electric charge, is equal to minus E. It's negative, but its value is this elementary charge we just talked about. If we measure this in units of coulombs, that's negative 1.6022 times 10 to the minus 19 coulombs. Okay, so that's how much charge is on an electron if we measure it in this new unit called coulombs. If we have a proton, it just has the positive value of that elementary charge. So it's positive E, or positive 1.6022 times 10 to the minus 19 coulombs. So that's the smallest amount of charge that's possible. But, you know, let's also give some other points of reference, right? Like if you were just to take a piece of plastic that you can hold in your hand, rub it with a cloth for a while, you might get like a microcoulomb of charge as a result of that. Are you all familiar with this unit prefix, micro? What is it in powers of 10? 10 to, yeah, so when I say microcoulomb, I'm just saying 10 to the minus 6 coulomb. Oh, I forgot it was right there. Yeah, it's right there. Okay. But you knew that already. You didn't need to see that. Or if you rub a piece of glass, you'll get positive charge about a microcoulomb. Right? So a coulomb of charge is a lot. It's a lot of charge. Okay? But that's just how the units work out. All right. Any questions on that? All right, so we're going to end it with a question for you guys to work on, and then we'll wrap it up. So here we go. An electron has a mass of 9.11, 10 to the minus 31 kilograms. That is the mass of an electron. The charge of an electron is minus E, which again is minus 1.6022 times 10 to the minus 19 coulombs. So these are numbers that are going to come up a lot. The charge and the mass of an electron are going to come up a lot in this class. So suppose that when you rub a piece of glass with a silk cloth, the glass acquires a charge of 1 microcoulomb. My question for you is, how many electrons must have been transferred in that process? So if we get 1 microcoulomb of charge, how many electrons, if we just count them up, is that equivalent to? It's a very large number, as you can probably imagine. And then here's the sort of a follow-up to that. Suppose you have 1 kilogram of electrons. How many coulombs of electric charge is in that 1 kilogram of electrons? So essentially, both of these are just sort of unit conversion problems, but try to work it out at your desk, and then we'll go through it. And did everyone bring a calculator today? I mean, you have one on your phone, right? Generally speaking, you should bring a calculator. So I know for this one, I'm probably not giving you enough time, but I'm just keeping an eye on the clock. And I have to take care of late ads after this, so I want to end a bit early. So I'm going to show you the solution to this, and then we'll wrap up the lecture, okay? So, as I said, you can really just think of this as like a unit conversion problem. In the first question, we started off with a quantity 1 microcoulomb. And I want to take that and convert it to some number of electrons. Okay? So, like with any unit conversion, we're going to multiply by a conversion factor. The first conversion factor is going to take us from microcoulombs to just regular coulombs. And what goes on top for that? 10 to the minus 6, right? Because 10 to the minus 6 coulombs is the same as 1 microcoulomb. That's what I'm showing you here. Now we've converted just to regular coulombs. And then lastly, how many electrons, or what's the conversion between electrons and coulombs? Well, in 1 electron, we have this much charge, 1.602 times 10 to the minus 19 coulombs. And let's just verify microcoulombs cancel, coulombs cancel, and we just have some number of electrons, okay? Does this make sense? And what does that, can someone actually crunch those numbers and tell me what it is?
6.24 times 10 to the 12.
6.24 times 10 to the 12. So in other words, like 6 trillion electrons or something, okay? Pretty large number. But it's worth noting that compared to the number of total electrons that are around, that's actually kind of small. So only a small number of the total number of electrons move over, but it ends up being about this much. Okay, the next is, we have a kilogram of electrons, and the question is how much charge is contained in those kilogram of electrons. So just think of this as another unit conversion, where the quantity we start with is a kilogram, and the quantity we want to end up with is coulombs, okay? So here, let's do this first. What is the mass of the electron? We had it on the board before. It's 9.11, 10 to the minus 31 kilograms for every 1 electron. And the next, so that takes us to a number of electrons, right? But we also know that for every 1 electron, we have 1.602 10 to the minus 19 coulombs. I know there's a negative sign there, but I'm trying to count it up, right? So we have kilograms canceling, we have electrons canceling, and then we end up with units of coulombs, right? And so basically, this is just like saying take the charge in coulombs, divide by the mass in kilograms. And what does that work out to?
1.762 times 10 to the 11.
Yeah, and I guess because we're talking electrons, that should be negative, right? So that's how we do this one. And that's where we'll end it for today. And we'll pick up on Wednesday with Coulomb's law, which explains exactly how the force of attraction and repulsion works.